All right, so we are going to do the last part of this chapter, which is Le Chatelier's principle. And that basically describes if you have a system at equilibrium, how does it behave when you disturb that system? In what ways can you disturb that system? And how does it behave when you disturb that system to reestablish equilibrium? Okay, so LCP, or Le Chatelier's principle, I'm just going to say LCP from now on, okay, says that when a chemical system is at equilibrium and when it's disturbed, the system will shift in the direction that minimizes the disturbance and it will try to reestablish equilibrium. Okay? So, here are the ways that you can disturb a chemical system. We're talking about a reaction here, an equilibrium reaction. Okay? One of the ways is to change the concentration of the reactants and products. You could add reactants, you could add some more products. That's one way. Okay? Another way is to change the volume or slash the pressure. If you remember, your gases, volume, and pressure are connected, right? And another way is to change the temperature. Most of the time, in order to make a reaction more efficient, you can do multiples of these to get more products or get the reaction to move more forward. Okay? So let's talk about each of these one by one. So this is the effect of concentration change on equilibrium, okay? So let's look at this reaction where you have nitrogen and hydrogen forming ammonia. This is called the Haber process. Very, very common chemical system to make ammonia, okay? So we are trying to change the equilibrium by changing the concentration, okay? Or we're trying to disturb the equilibrium by changing the concentration. So, one of the ways that you could do to push the reaction to go more towards the product, which is the ammonia, is you can add H2. Now, before you add the extra reactants, your Q is equal to your K. Remember, when Q equals K, you're at equilibrium, okay? But immediately after you add the H2, your ratio of products over reactants, now you have more reactants than you would have when Q is equal to K. So now Q becomes smaller than K, okay? Because you have added more reactants. So if Q is smaller than K because you added more H2, the reaction is going to shift to the right to reestablish equilibrium. Now, if you add N2, the same thing would happen. If you add more nitrogen, the reaction will shift towards the ammonia to use up that extra reactants that you added to form more ammonia to reestablish equilibrium. Okay, so here is a graph showing what happens. So the green line represents the hydrogen, and then the red line is ammonia, and then the blue line is nitrogen. Now, what's interesting here is this little point here, or this little thing here, that's where you just added hydrogen, okay? So you'll see a big spike of H2 that then slowly goes down until equilibrium is reestablished. And you can tell these are partial pressures because these are gases, right? So the partial pressure of H2 is like here, and the partial pressure of NH3 is here, and the partial pressure of N2 is here. And this is when the reaction is at equilibrium. Then you see that big spike in the partial pressure of H2 when you add more H2, and then the H2 gets used up. And when equilibrium is reestablished, the partial pressures of all three are, well, of H2 and NH3 is higher, but the partial pressure of N2 is lower. Okay, so you see the big spike, and then the H2 gets consumed, and then you see a little bump when the ammonia is being formed. More ammonia is being formed because you just added more H2. But since you did not add more N2, the partial pressure of N2 decreases slightly because you are using up whatever was left of the N2 even more. Okay, so N2's partial pressure is lower when equilibrium is reestablished, but H2's partial pressure is higher than before, like slightly higher. See where it was before? So that's the difference. And then NH3's partial pressure is also slightly higher, but N2's partial pressure is slightly lower. Okay? So the addition of H2 resulted in the production of more NH3. The reaction got shifted forward, more products were made, and in the making of more products, the partial pressure of N2 dropped because more of it was consumed. Now, if you do the reverse of this, if you added ammonia, you would see the reaction shift towards the reactants in the reverse direction, because in that case, Q would be greater than K. You would have more products. If Q is greater than K, that means you have more products at equilibrium. You have more products than you would have at equilibrium. So in that case, the reaction would shift in this direction, re-establishing equilibrium, and you would probably have slightly higher partial pressures of all three things, because you would have nitrogen increase, hydrogen increase, and you would have some of the ammonia that's still slight increase in partial pressure. Okay, now that is what would happen if you add reactants and products. Now another situation is for the same reaction. Yeah, I'll write out the same reaction. You have N2 plus, I believe it was 3H2 going to 2NH3. 2 times 3, 3 times 2, 6. We got it. All right. So here's another thing that you can do in order to um, make more products. So if you want to keep this reaction going, okay, because what you want to ultimately end up with is ammonia. So what you can do is not just add reactants, but instead of just adding reactants, you can start removing products. Okay, what if every time some amount of partial pressure that equals to ammonia was made, you keep venting it out, like you keep removing it from the chamber where ammonia was being made? That means if you keep removing the ammonia, you are basically pushing the reaction forward, because more N2 and H2 would combine to form more ammonia to reestablish the partial pressure that was removed from the ammonia. Okay, so not only can you like add reactants, you can remove products to just keep this reaction constantly going this way. What you're really doing is you're not letting equilibrium establish, because you're not letting the rate forward and rate reverse equalize. You're just removing the product constantly, and you keep adding the reactants. You would just keep the reaction going forward. Okay, it's not allowed to form, or it's not allowed to reach equilibrium. Now, another thing that could happen is if you wanted to slow this reaction down, you could remove some of the reactants, and then the equilibrium would shift this way, where ammonia is now being turned into N2 and H2. Okay, so LCP basically means if you take away from the product side, the reaction will shift forward to replace those products. If you take away from the reactant side, reaction will reverse in order to reestablish equilibrium to replace those reactants. Okay, it doesn't mean that all of the original concentration will be restored. It'll go to such a point where the ratio between them will be the same equilibrium constant. Okay, you can achieve that ratio without having those same numbers. Okay, so um yeah, okay, so here's a summary of what happens. The effect of concentration changes. Increasing the concentration of one or more of the reactants will give you a Q that is less than K. It causes the reaction to shift to the right towards the products. So giving more reactants pushes the reaction forward towards the products. Increasing the concentration of the products will make Q larger than K. Now you'll have more products than reactants, so the reaction will shift in the reverse direction towards the reactants. Here's the other thing you can do. Decreasing the concentration of the reactants will shift the reaction left or in reverse, like you're removing the reactants so the products become the reactants. Q will be larger than K at that point. Or if you decrease the concentration of the products, you are constantly keeping the reaction at Q being less than K. So the reaction will shift to the right or forward towards the products. Okay? So adding reactants or removing products achieves the same goal, or removing reactants and adding products achieves the same goal. Okay. Now let's talk about volume slash pressure. Okay. So same equation, just so we can see what happens. In this equation, on the reactant side, you have 4 moles of gas. And on the product side, you have 2 moles of gas. So if you have this reaction happening in a chamber and you increase the pressure of this system, what's going to happen is you're going to disturb the equilibrium by adding more pressure. The reaction shifts to the side where it has a lower number of moles of gas. And it's not just this, it's anything. If you have a reaction where you are increasing the pressure, the reaction will shift towards the lower number of moles of gas. Okay? So you go towards the products because products produce lower number of moles of gas because the nitrogen and hydrogen are being consumed. Okay, so the reaction shift towards the products. And if you decrease the pressure in this reaction, the reaction is going to shift towards the reactants where there are more moles of gas or the higher number of moles of gas to reestablish that equilibrium partial pressures. Okay, so your reaction will shift right when the pressure is increased in the direction where there is a lower number of moles of gas, and it will shift towards the higher number of moles of gas when the pressure is decreased. Okay, the right or the left really depends on which side has more moles of gas. In this particular one, right has lower number and left has a greater number of moles of gas. Okay, now here is a summary. Decreasing the volume causes the reaction to shift in the direction that has the fewer number of moles of gas, okay? Decreasing the volume is also increasing the pressure. I just read that wrong for a second. So decreasing the volume means increasing the pressure. So I'm going to say increase pressure. And so the reaction will shift where there's less number of gas and less number of moles of gas. And then increasing the volume or decreasing the pressure causes the reaction to shift in the direction that has the greater number of moles of gas. So more space means it's going to shift in the direction, whichever direction that has a greater number. Okay? Now, it gets slightly complicated when we start to keep one of those things constant. Okay? So I'm gonna, this is basically saying the same thing, okay? This is important. Oops. This is different. This part. If a reaction has an equal number of moles of gas on either side, the volume has no effect on equilibrium at all. The change in volume has no effect on equilibrium if either side has the same number of moles of gas, okay? But here's a different situation. This one is a little more complex. What if you add an inert gas that has no bearing on the reaction? It's not going to react with the reactants. It's not going to react with the products. So there are 2 situations where you can add the inert gas. And these are the 2 situations, okay? You can either add the inert gas at constant volume, or you can add the inert gas at constant pressure. Those are the 2 situations. Now, let's talk about what happens when you add an inert gas at constant volume. When you are reading a question for LCP, be very careful to note if it's a gaseous question, whether it's at constant volume or constant pressure. It's going to change based on what the situation is, okay? Now, if it's kept at constant volume, meaning you have a rigid container, think of like a metal tin, okay? You're not changing that container, like a very hard metal tin. The gas is inside, the volume is constant, the volume is not changing, okay? When an inert gas is added to the system at equilibrium at constant volume, when you add more gas into this tin that is constant volume, the total pressure of the system is going to increase. Okay, that's true. Because if you take into account all of the collisions happening inside this rigid container, okay, here are some reactants, here are some products, okay? And now I'm going to add an inert gas. Oh, when I say inert gas, so this is the inert gas, the red dot, I mean like one of your noble gases, okay? Like, I don't know, xenon or neon or argon or something, okay? We're talking about those gases that don't react with anything really, okay? If I add a bunch of inert gas to this, so I had green and black particles before, now I've added the red particles as well, the total pressure is definitely going to increase inside the container. But the container cannot respond. It's not a balloon, right? It's a rigid container. So it can't respond to that increase in pressure. So the volume is constant. This is rigid. And the volume is constant. Constant volume. So think about the concentration of the gases inside there. The total pressure increases, but the concentrations of the products and reactants or the ratio of moles to volumes does not increase. Let's say I had 5 moles of the gas inside 1 liter, okay? And I had, I don't know, 10 moles of the green particle inside 1 liter. The volume does not change because the container is rigid. So the concentration of the reactants and products have not changed. And because of that, when an inert gas is added to the system at equilibrium at constant volume, you're not affecting the concentration of the reactants or the products. It's just more pressurized in there, but there will be no effect on the equilibrium. Okay? It's just a tighter fit, but since the inert gas is not reacting with the reactants or the products and the volume is staying constant, the concentration stays constant, no effect on the equilibrium. Inert gas, constant volume, no effect on equilibrium. Okay? Let's talk about the addition of an inert gas at constant pressure. When you add an inert gas to the system at constant pressure, trying to keep the pressure constant, then the total volume will increase. Like if I want to maintain the pressure at like some number and I add more particles, I have to increase the volume to keep the pressure constant, okay? So the volume will increase. So the concentration of the reactants and products will change. It'll actually decrease. So the equilibrium, because you have a greater volume for the same number of moles, okay? So the equilibrium will shift towards the direction in which there is an increase in the number of moles of gas. Because now you have decreased the concentration, it'll go towards increasing the number of moles of gas, okay? This is much easier to see it if you like do it kind of mathematically. Hold on, I want a new slide here. Discard. I'll put in a new slide here. There we go. All right. So here's what could happen, okay? Let's come up with a generic equation. I have one here. This is going to be A going to B plus C, okay? And my equilibrium constant is equal to just 1. All right? Because that'll give us like equal amounts of, well, what happened? What did I do? Hold on, guys. That's great. Fast forward through this, okay? I don't want to, oh, there we go. We got it back. Fast forward through that part because I don't want to like split and edit that part. So just fast forward, okay? All right. So back to our equation. We have Kp equals 1. If Kp is equal to 1, let's write our equilibrium expression. Concentration of B, oh, not concentration, we're dealing with gases, so partial pressure. Mistake. Partial pressure of B times partial pressure of C over partial pressure of A. Okay? So this is going to just be 1. If that's the case, we can say, I'm going to say the partial pressures of each thing. Partial pressure of A is equal to partial pressure of B, and I'm going to say partial pressure of, and that's equal to partial pressure of C, and I'm going to say all of this is 1 atm. Okay, that'll give us a Kp of 1. Now, if all of the partial pressures are equal, that means you have 1 atm from B, 1 atm from C, 1 atm from A. That's going to give us a total pressure of, so your P toots is going to be equal to 3 atm because each atm is coming from each of the gases. Okay, if we add an inert gas to this mixture, okay, at constant pressure, add an inert gas at constant pressure, the container is going to expand, okay, to accommodate that extra pressure, and therefore the volume will increase, okay? Your P total cannot change because we want to keep the pressure constant. We want to keep it at 3 atm. So the partial pressures therefore have to change because now you're adding an inert gas to the mix, okay? So let's add inert gas D, okay? I'm going to say the inert gas is D. If we add inert gas D, like xenon or something, okay, then the partial pressure of A is going to be reduced. So is the partial pressure of B. So is the partial pressure of C to accommodate for the partial pressure of D. And I'm going to say, because the constant pressure has to be, it has to be 3 atm, then A, B, and C got reduced to accommodate for the fact that the total pressure is still 3 atms. Okay, so when you add an inert gas, okay, you end up decreasing the partial pressures of the reactants and the products because of the fact that you have to keep the pressure constant, but the volume increases. Okay, so now all of them are 3/4 of an atm because that adds up to 3 atm. Okay, P total is still 3 atm. And if you calculate QP now, well, is that what I did earlier? Anyway, if you calculate QP now, let's use orange because that's pretty. QP is now partial pressure of B, partial pressure of C over partial pressure of A. This is going to be 3/4 atm, 3/4 atm over 3/4 atm, right? So QP is just going to be 3/4. 3/4 is less than 1, which is the equilibrium constant. So if QP is less than 1, that means the reaction will shift towards the equilibrium. In this case, to achieve equilibrium, you'll end up making more products. Okay? So if you add an inert gas at constant pressure, the partial pressures of those gases that are in the reactants and products will decrease, not because they're reacting with the inert gas, but because the volume increases. And when the volume increases, the ratio of moles to volume, right? Now you have a greater volume that is affected. So the partial pressures will decrease and the reaction will shift towards, and your QP is now less than K. The reaction will shift forward to make more products to reestablish equilibrium. Okay, so that is what would happen. Inert gas, constant pressure, volume increases, partial pressure decreases, reaction shifts forward. Okay, all right, so that was that. Just fast forward through that middle bit, all right, where like the tech thing happened. Anyway, I honestly don't know what happened. I don't even know what I touched. Okay, so let's, last thing, disturbing the temperature of the equation. Okay, give me 1 sec. Okay, I'm recording something. The effective temperature change on equilibrium. Now, you have two types of reactions. You have exothermic ones and endothermic ones. So you should think about the thermal energy generated, like released or absorbed, as either a reactant or a product. So if thermal energy is released in a reaction, you should think of it as a product. And if it is absorbed, like the net amount, okay, if it's an endothermic reaction, you should think of that thermal energy as a reactant. Now, remember, every reaction absorbs heat and every reaction releases heat. It's the net. If more is absorbed than is released, then it's endothermic. If more is released than is absorbed, like from the forming of new bonds, more is released, potential energy being turned into thermal energy, then it's an exothermic reaction. Okay? So, for an exothermic reaction, increasing the temperature is very similar to increasing the products. So imagine you're releasing heat. If I heat the reaction that is releasing heat, it's going to not like that. It wants to release the heat. So if you give it heat, it's going to be like, I am trying to get rid of heat. Why are you giving me more heat? And it's going to not like that. Okay. So if you give heat to a reaction that is releasing heat, you're going to make the reaction go in reverse towards the reactant. If you heat the reaction that needs more heat, like it likes it, okay, it's endothermic, then it's going to shift forward towards the products, okay? So you want to heat endothermic reactions and you want to cool down exothermic reactions in order to get more products, okay? So this temperature is actually very important. Temperature changes in concentration, pressure, volume, that does not affect the equilibrium constant, but changing the temperature actually affects the equilibrium constant. Okay, so let's look at exothermic reactions. Increasing the temperature of an exothermic reaction, the reaction absorbs more thermal energy and then it'll shift towards the reactants because you are basically adding products. It doesn't like it. Then, if the reaction is at equilibrium, it's going to act in a way to lower the temperature. So the equilibrium constant actually becomes smaller. Okay. The new equilibrium mixture has more reactants and fewer products. Decreasing the temperature of an exothermic reaction, meaning you're going to remove the heat from this reaction, causes the reaction to shift right. The reaction releases thermal energy, okay, and it's going to produce more products. The value of your equilibrium constant increases. So you want to cool down an exothermic reaction to make the K larger and to get more products. Like it'll literally drive the reaction to a new equilibrium constant that is larger, which means you'll get more products, okay? And if you increase the temperature of an endothermic reaction, that's also good because that's like adding more reactants. You're pushing the equilibrium to be larger and you'll end up getting more products and the actual equation also shifts more towards the forward direction. Okay? The K value actually increases if you heat up an endothermic reaction. Cooling down a reaction that requires heat is not good. The equilibrium constant will get smaller and the reaction will shift towards the reactants and you'll stop making as many products, you'll get more reactants. Okay, lower amount of products, the value of K is lowered. Okay, so changing the temperature actually pushes the equilibrium constant based on whether it's exothermic or endothermic. For endothermic ones, if you want to make the equilibrium constant larger, you got to heat it up. For exothermic ones, if you want to make the equilibrium constant larger, you got to cool it down. Okay? So be careful about reading and interpreting what's going on in the reaction. It's just the attention to details that's going to matter. Okay? So here's the summary. This is basically what I just explained. You can read it on the PowerPoint on your own.